and I want to thank you all for attending our seminar today on best printed circuit board layout practices for successful manufacturing. A couple of housekeeping items before we get started. I just want to let you all know that you will be muted during the presentation. If you have questions at any time during the presentation, please enter them into the question panel located in the webinar control panel on your screen, and we will try to get to those questions at the end of the presentation. Also, for your information, we will be recording this webinar and we'll be posting both the recording and the slides on our website and YouTube channel. Our presenter today is Al Wright. He is our printed circuit board field applications engineer. Al has been with Epec for 12 years and brings in total well over 25 years experience in printed circuit board design. In fact, by our estimation, Al has been involved over the years in over 50,000 individual design efforts, and it's that extensive experience from which he's drawing and passing on to you today. Al, with that being said, I'll turn it over to you.
Okay, thanks, John. First, I'll go over the agenda. Welcome, everybody. What I'll be going over is I'll give you a brief description of Epec's typical front-end workflow from our quotation through pre-production engineering. Then I'll do a couple slides on the importance of getting complete information for accurate quoting and job setup. I'll describe how we do our automated design rule checks and how we do our error reporting to you if we find anything. Besides the automatic checks, we'll be looking at design choices to avoid and what you want to do instead. And then at the very end, we'll do resources for success, some places you can look for more information, and some questions and answers that you can enter as they occur to you, and we'll have a Q&A session at the end. So first off, it's good for you to understand Epec's front-end workflow. It begins with an accurate quotation, and this is hopefully based on complete and accurate information that you supply. And once you've decided to go with Epec and we receive a PO, we select an appropriate production facility based on your design complexity and your delivery requirements. And then the order moves into a pre-production CAM queue, that's computer-aided manufacturing. And here we perform design rule checks and we manipulate your data files as required to ensure that there won't be any holdups once the boards enter the manufacturing stage. So we're basically just making sure it's kind of goof-proof. So can't stress this enough, an accurate quote starts with complete information. So when we receive incomplete information and then we find out later about important requirements that we didn't have available at the time of the quote, we have really no option but to go back and revise our quote, and unfortunately it seldom gets cheaper from there. So it's good to get us complete and accurate information at the beginning. Otherwise there are delays. It's an uncomfortable situation for everybody. When you do supply complete information, it enables us to price your product accurately right from the beginning. And what this means is that you can make your purchase with confidence that the pricing isn't going to change after you've placed your order. And you can also do good comparison shopping if everything's complete. So in order to know what's complete, I'll define it. A complete set includes Gerber files for all the layers, and this would include all the copper layers, all the solder mask layers, the component silkscreen layers, solder paste layers. A lot of people leave those out. We like to get them. A PCB outline in Gerber whenever possible. We also need to see an Exelon format drill file, which is basically an ASCII text file. You can open it in Notepad or WordPad. And that's another thing that we often do not receive with the initial data package, and it's very important that we do receive it. And another thing I want to mention that I'll get back to later, the decimal resolution for all these Gerber files, you want to write everything out in at least 2.4 decimal resolution. Don't use 2.3. There are still some systems that default to 2.3. You don't want to use it, and I'll get to that in a little while. Something of a lost art these days is a fabrication drawing. We receive fewer and fewer of these, but they're great to have because they define the outline, the key dimensions, the hole locations. You want to use notes to define the PCB thickness, the surface finish, material type, ink colors for solder mask and silkscreen, any stack up or impedance requirements, and even panelization layout if you have one that you want to use. This drawing can be a Gerber, it can be in DXF format, or even HPGL. PDF drawings are acceptable, but we can't import them into our CAM program, so they're not ideal, especially if you have a complex outline. We would need to recreate that dimensionally, and it's just much better to get a vector format thing like DXF or Gerber. And if you can't create a fabrication drawing, please supply us with a README type text file, which includes most of the same information. And between that and the Gerber files, we'll be able to understand what you're wanting to build. Other information we like. If we can get an IPC D356 format netlist file, this enables us to verify that your Gerber output files match the electrical requirements for the circuit. This is a great spot check for making sure that we don't have any problems importing your Gerber that corrupts your electrical integrity. So try to export one of those and send it to us whenever possible. There's actually a picture of one on the right, another file you can open in a text editor, and it explains what some of that information is. It's just vias and component locations and so forth, electrical connections. You also want to inform us of any special testing requirements like high plot testing, PPAP, automotive or aerospace specifications, anything that's going to potentially add to the delivery time or the price. We don't want to surprise you later with an extra charge that you hadn't taken into account, but we need to know all the requirements. And if the product is ITAR controlled or for some reason needs to be manufactured in the USA only, then please express this at the time of the quote too. A lot of times we quote things and then we don't find out that they're ITAR restricted until we see the purchase order, and then we have to adjust, and we don't like to do that. So now that I've gone through all that, the engineering people among you will be more interested in this stuff, like what we actually do. What are our initial checks? When your order moves into the CAM department, first thing we do, we load the files. We check to be sure that we received all the information we need. And usually by the time it gets to that point, we have everything together. At that point, we assign the layers different types, like copper layer, solder mask layer, to explain to the system what the function of each layer is. And then from that, we create a reference netlist, which is our CAM program's interpretation of the PCB's electrical path based on the Gerber. If we received your IPC netlist file, we run a comparison of our system-generated netlist to your file, and they should match 100%. We will report if they don't, and it's also a good idea if you have like known shorts or something, put those in your README file or on your print, and that way we won't stop to ask about them. Some people do have shorts that they know about ahead of time, so communicate those. And then we do a spot check for items like dimensions, hole quantities, etc. We make sure that there are no obvious discrepancies like scaling errors or something. And you can see at the right, I've done a manual spot check of this 6.226 dimension by measuring from point to point. That's that white rubber band line. And the distance checks out at 6.226, so that particular spot check is ready to go. And that's a manual check. now we run automated design rule checks, and this is a kind of a page on our website that describes what our design rule minimums are over on the right. Once we're sure that the data files are complete and valid, we run a series of these design rule checks for minimum spacing, minimum feature sizes, annular ring, and so forth. If you notice at the right, many of these minimums increase with copper weight, and that's because heavier copper requires wider design rules. So you'll see over by my arrow here, my pointer, interlayer line width on 1 ounce copper is different from the one on 2 ounce copper. It's different from the one on 3 ounce copper. So keep in mind what your copper weight is when you're deciding on your design rules. Now, to find out ahead of time whether your design will comply with our design rules, you may view this sheet on the right on our website, and I've provided the link here. Or you can download our entire PCB design guide from this address right here. So those are very good resources for understanding what our capabilities are ahead of time. If you find anything where our first priority is to keep your order moving. So if we find something small that's easily resolved, like a conflict between the instructions on 2 different documents, the first thing we'll do is we pick up the phone, and if it's something we can just have a 2-minute conversation about and move on, that's the best thing for everybody. But if we do find an inordinately large set of critical issues that the system has flagged during the design rule check, you'll receive an email which may include a report like the one below. This report explains what we found, and it gives a brief description of why it's a problem. We do make every effort to ensure that we look at the entire design before we put anything on hold or before we submit a report to you, because there's nothing more annoying than receiving one question and then 2 hours later another question and 2 hours later another question, and then you're into the next day. So we try to compile all this at the same time. We also realize that a lot of our customers are contract manufacturers. If you have any problem interpreting that, you can just pick up the phone and call us. Otherwise, you can sort through it, and we can all figure out what we'll do about it. And why do we ask so many questions? We actually don't like placing things on hold, because each job on hold is another thing for us to manage. So why do we do it? The answer is that we're responsible for meeting all of the requirements stated in your documentation. So this means we need to resolve conflicts when they occur, because only one thing can be right at a time. So if you say the board's 047 thick on one document and 062 thick on another document, we need to resolve that right at the beginning, because it'll affect some of our design rule checks, and it will also be something we're going to have to certify later on our certificate of compliance. So again, only one thing can be right at a time, so we need to know what it is. So we will ask things like that. All right, so getting at last to some of the actual DRC-based enhancements that we do, and these are things that we do just to make the board more producible. They're not major design changes, and they're usually intended to address some particular defect that would be caused if we didn't change them. And the first 1 or 2 of these will be things that we do pretty much automatically. We don't bother you asking, because they're just industry standard things. So The CAM program basically runs a design rule check by comparing your Gerber to an internal file in the CAM program that we've populated with definitions of the PCB's requirements, and then it flags any violations it finds. And again, if we can easily correct these without fundamentally modifying the design, we typically perform the edits and we just continue. Some of the edits include fixing common minor violations like reference designator ink falling onto pads. This is a rejectable condition because you won't be able to solder your board if there's ink all over the pads. So we do what's called a silkscreen clip. And if you look up above, you can see the red is the silkscreen, and it's running over some of the pads, and it's too close to some of the other pads, and it could end up getting on them. So we trim it back by a defined limit, by a defined amount, in this case 6/1000ths of an inch, and that just prevents the ink from getting onto the pads, and it's also usually enough to not obliterate the silkscreen. So it's a good compromise between removing too much and leaving it alone and having ink all over the pads. Here's one of the rare times when we would actually modify the copper without really asking about it, because this is an extremely minor change and it's just based on manufacturability. So what you have here next to this X is a little sliver of what would be film resist in between the trace and the pad. And you can see instead of coming down here and going into the pad, it's leaving this little sliver. And if we don't modify that, the resist film could actually flip up off of there and migrate around and stick somewhere else and create a bridging short. So that's not good. And if the film doesn't peel off and migrate, what happens is etchant can get trapped in this little narrow area, and it will continue to eat away at that short line segment, and you could get a board that passes electrical tests, but that actually ends up having the trace eaten away, or it's so compromised that when you thermally shock it later at assembly, it'll blow like a fuse. So you want to look for acid traps when you're designing your board, and here's what we do to correct it. We just drop a little piece of copper right into the sliver, and that eliminates the whole mess. Some things don't actually get caught by design rule checks. So here's a questionable design practice. It's harmless to us as the bare board manufacturer, but it can cause problems later at assembly. Now, if you notice, the orange in here is the metal pad, the green is the solder mask, and the blue is the trace coming into the pad. If you notice, 3 of these traces are wider than the pad itself. So when the solder mask is cleared here, what happens is you apply your solder paste at assembly the same size as the pad here, but it will then be able to migrate onto this exposed metal where the blue is, and you could get a bad solder joint because you just don't have enough solder on there. So it's really a good idea to avoid this kind of configuration, and if you need to run a fat trace into a skinny pad like that, you might want to do it from the side, or you might just want to make sure that you neck them down so that they're no bigger than the width of the pad, like this one where my arrow is. Here's another thing that doesn't really cause us any problems, but it might cause you a minor problem later at assembly. And it's basically a grossly oversized thermal pad. Now, thermal pads are kind of misnamed because they're really for thermal containment. They have these air gaps around them so that the pad stays nice and hot while you're soldering them, so you don't have as much copper going directly to the surrounding plane, acting like a heat sink. Well, if you have a very large thermal pad like this, that pad can act as a heat sink, and you could get a cold solder joint in there. It's not all that likely, but it's something to avoid. It also plays havoc with things like cross sections when you're looking at the cross section and the pad size is varying wildly from one layer to another. And just today I had a situation where there were some vias placed in the air gap of a large thermal like this. They shouldn't have been anywhere near the thermal because the thermal should have been much smaller. But check your system. This is something you'll find in your pad stack definitions. Try to make the inner diameter of your thermals the same as the diameter of the outer layer pad, or maybe a mil or two larger. Keep it proportional to that pad, though. Don't have a giant internal pad and a small external pad. There's really no point to that. And it can lead to some other grief, too, with not having enough room to place vias on the internal layers, too. Here's something I mentioned right at the beginning of the presentation, and this is a resolution error. If you see at the right, you see this pad and this pad. The holes are not concentric within the pad. And believe it or not, that's just because the fourth digit to the right of the decimal point in your Gerber files, or actually, yes, in your Gerber files, was truncated off because it was written out at 2:3 resolution. And what happens is that the pads then have what are called rounding errors, and they justify to the nearest thousandth of an inch. This doesn't seem like such a big deal, but if the annular ring is very tight, it will cause, this little offset will cause an annular ring violation. And if you have, say, 1,500 vias per layer, and 700 of them are coming up with violations because of this, that's not a good situation for anybody, because we'll end up flagging it and asking you about it. So just remember to export everything at least 2.4 Gerber resolution and drill resolution, and this shouldn't happen. We actually recommend higher resolution like 2.5 or 2.6, and that's got more to do with things like polygons resolving properly, but 2.4 is your absolute minimum. Here is a situation that comes up with BGAs. Some BGAs, there's enough real estate so that you can still on the pads that have the holes in them. Because what can happen is you can get solder bridging during assembly where the solder might blow across and actually short these two things, and that's a short that's going to be occurring under a BGA, and that's kind of an ugly situation for an assembler. So what we generally recommend is either mask over these completely if you're comfortable with that, or if you're not comfortable with that and you want the hole to remain open, do what's called an encroaching solder mask opening, and as the name would imply, you encroach on the pad with the solder mask. So this area would be solder masked all around the edge, and then the opening would be 0.03 of an inch all the way around the via. That leaves the via open, but it increases the distance between the solder mask openings so that solder can't migrate. And that'll really help your yields at the assembly stage. Your assembler will thank you if you do that. Lately, an awful lot of boards require impedance control, but we don't always get all the information we need here, and this can cause a lot of lost time. So here we have a customer who had asked for impedance control on the 5 thou lines on 5 different layers, and they wanted 100 ohms differential. But they didn't specify the spacing value for the distance between the lines, and you need to know that to calculate the differential impedance. So we had to try to go looking for them to see if we could find out where they were. Unfortunately, all of the lines that you see here highlighted in white are all 5 mil lines, and a lot of them run roughly parallel, but if you look close up on them, they're not really running parallel. So our only way of checking to find out where these differential pairs is to scan around, zoom in, actually take measurements, try to go up and down the line, see if the spacing varies. And that's incredibly time consuming. And you know, we like to try to do that before we ask a question, but eventually we do have to ask a question. So eventually on this one, again, we were supposed to find differential pairs on 5 different layers, but we only found them on 3 layers. But we couldn't really be sure that we hadn't missed something because of all the different 5 mil lines on the layer. So again, we're obliged to ask because we need to certify that the impedance is correct. And since it says it needs to be correct on 5 different layers, we're supposed to report on 5 layers, but we can only find it on 3. So it turned out that the designer only had 1 differential pair per layer, and that he only had them on 3 of the 5 layers. So we eventually resolved that. But it took some time. And he had to revise his documentation or write us a waiver or something. So information that's required for impedance control, here's what we like to see. The layer numbers where the traces occur, what the trace size is, what the target impedance is, what the spacing is, if there's differential impedance involved, what reference planes are involved. And here's a hint that really helps us, because we occasionally need to make micro adjustments to impedance traces to get the impedance dialed in, because we don't have the ability to make infinite adjustments to the dielectric thicknesses, because that stuff comes in sheet stock and it only comes in certain thicknesses. So sometimes we need to adjust the trace. It's a lot easier for us to find the traces and to make those adjustments if you segregate them by not making them all the same size as the rest of the traces on the layer. Usually what I encourage people to do is make the impedance layer, the impedance control traces, like these would be a 5 and 5 pair, and then all these other 5 thou traces, make them 4.99 or something like that. Just take 1/10 of a thousandth of an inch off of there. Then when we highlight this trace size, the only thing that will pop up is the differential pairs. It makes it a lot easier to find them, makes it a lot easier to make those micro edits. And I'm saying edits, but they're not really significant edits. They're just very small micro adjustments, as I said. So the last thing is a few tips on what I call participating in your own success, so that your designs will be clean and complete, and you'll get what you expect when we build your product. First thing is double check your documentation for errors and conflicting information, like I spent some time on at the beginning. If you're on support, use your software developer of your CAD program for advice on how to change settings like pad stack settings or solder mask sizing or anything like that. You can also sometimes find user groups online. Informal user groups are good because they're not necessarily moderated by the developer, and you know, everybody might be complaining about the same thing and maybe somebody's found a fix. So that's a good outlet. You also want to familiarize yourself with the industry guidelines. In particular, if you're a designer, IPC 2221 is the generic design spec, and that has a lot of recommendations and a lot of descriptions of how to ensure a good result. And then 6012, which is qualification and performance. 6012 and the inspection specs 600, IPC-600, those are closely related. 600 is more pictures of defects and sort of a go, no-go guideline, and 6012 is a little bit more texty with some tables. I like 6012 for figuring out how to do things when, you know, what the rules are for doing certain things if I don't know them off the top of my head. And lastly, you know, refer to Epec's website. You can also read our blog. We have a blog on a lot of different topics where I might not have gone into complete detail here. We have a PCB design guide. Actually, we have design guides for all our products, and we have an e-book that I participated in that covers some of the other defects that I didn't have time to cover in this particular presentation. I could sit here and talk all day about every little thing that could go wrong, but in that ebook, I concentrate on some of those defects that maybe aren't caught by our initial automated design rule checks, but which can cause you problems later. So that's definitely a good thing to read. And finally, don't be afraid to ask questions. We will attempt to answer any question that you want to ask, and nobody was born knowing everything, least of all me. You know, I learn 5 new things every day after all these years, so there's no reason to be intimidated by anybody. And my finding, and most of you probably would agree, it's easier to avoid a problem by anticipating it than it is to fix one. So anything you're not sure about, ask a question, and we'll be happy to help. And that is about it for me. I'm going to hand it over to John Stabers for now.
Thanks, Al. Appreciate your sharing that presentation with us. While Al reviews the questions that were submitted during the course of the presentation, I just wanted to point out that these other product families that you see are also Epec offerings. And as we've done here and have done in the past and will continue to do in the future, we're going to continue to send out invitations for webinars on these various areas where we'll share some of our engineering expertise. Next slide, please.
Okay.
And just so that you can see from a design and technical support standpoint, we have locations throughout the states, in Canada and in Europe, and again, each of those outlets offer local support and really detailed product management and product design support for your benefit. As I mentioned, we'll continue to send invitations and conduct seminars in the future. So that said, I'll give it back to Al so he can address some of the questions that were submitted.
Okay. All right, I'm picking through these. There's quite a few. Okay, well, here's one that gets back to one thing I was already talking about, but why don't the automated DRC checks catch some of the errors you describe? So I guess that's, why aren't they caught automatically, and why is it that maybe we catch certain things visually just because we know that they might be a problem? I guess the answer to that would be that the systems that we use are designed for us to produce the board pretty much as close to how you design and order it as possible. We assume that it's been designed correctly, and most of the checking we do is to be sure that we identify any condition that's going to cause us to scrap the bare printed circuit board before we ship it to you. Like, if we see the spacing's too close, that could cause shorting, or we see the traces aren't really parallel, we'll report that to you because the differential impedance won't run right. But those checks don't always catch certain things that might bite you at assembly later, like especially solder migration issues. There's a lot of solder migration issues that can occur if you have things like vias coming too close to surface mount pads, and having solder mask clearances on both items. I would encourage you to look at that ebook that we have on our website, because it's got 10 or 11 kind of classic defects on there, and a lot of them are of this type that aren't caught by the automatic design checks. They're just things you kind of need to know when you're laying something out. And I know I've really helped out one of our assemblers, because one of his end customers was doing about 5 of those things chronically. And now that they've started designing things more cleanly, the assembler is just getting much better throughput, because he's not stopping and fixing defects that never should have occurred in the first place. So that's really why they're not caught by automatic checks, though, that they're not really going to cause us any problems in production. But again, they could cause you problems at assembly, or cause problems for your contract manufacturer at assembly. Julie will like this one. About how much of the information you receive is incomplete. Well, that's hard to say, but anecdotally, our customer service department at the quoting stage says that we get complete data that enables us to quote the board accurately about 60% of the time. So that means when we get a quote, when we get a data package with a quote, we usually have to stop and ask the purchaser 40 to 50% of the time for some information that's missing. And, you know, that just makes it a little bit more difficult on everybody. So some of the classic things to be missing, I touched on some of them in the presentation, like missing fabrication drawings or missing fabrication notes, missing contract review items like ITAR control or certain testing things that need to be done. Another thing we often don't see is panelizations. Like if you're going to be assembling your board in panel form, it's really good for us to know what that panel needs to look like when your purchaser orders the board, because if we don't, then we're going to design our own panel just for the purposes of quoting. We're going to design it based on our own preferences, and then maybe a competitor is designing to their preferences something completely different. So the problem then becomes when everybody presents their pricing to your purchasing department, it's not really based on the same set of guidelines. So you're not making an accurate, informed decision about apples to apples pricing. That's something that happens a lot. So it's a good idea to coordinate with your purchasing department as much as possible if you're an engineer or a designer, and make sure that they have full access to all the information related to the order. Make sure that they get their complete files from you. Be sure to communicate anything to them, like if you're ordering, if we're like your second source, you've built the board before, you've had problems. Sometimes we get asked a question, oh, we've had problems with this board before, and that's all we're told. Make a little description of the problem you've had, and we can analyze the design to see if it's a design-related problem, or maybe your previous fabricator just isn't doing a good job for you, and we'll be glad to tell you that. But you know, the more information, the more detail you can supply, the more accurate your quote's going to be, the less likely there will be holdups, and you know, everybody will have a lot less stress in their lives. And I think I'm running out of time here a little bit. So what I'll do is some of these other questions that are coming in, I'll get back to the people who are asking them by email at some point in the very near future, the next couple of days, and hopefully we'll get everything answered. And again, you'll have other questions, but do look at our blog, do look at our ebook, do look at our design guides. There's a lot of information in there. It may not answer your question, but it may help you to direct your question, and then when we talk, we'll be able to figure out exactly what we need to do to get your boards built the right way the first time with no delays.